Now we've been talking about derivatives for a while, and there are at least two different occasions where I let slip and say, instead of just saying the derivative, I said the first derivative. And the reason why I let that first derivative slip out is because there's no reason to stop at differentiating a differentiable function at just one time. As long as the derivative is also differentiable, we can just keep finding more and more derivatives to learn more and more about the function that we're interested in. And so in prime notation, we can think of the second derivative. Well, I should say we just take the second derivative and we illustrate it with an additional prime. So here's a function. We've got f of x is equal to x squared plus 4x. By now, you know that the derivative is equal to 2x plus 4. Let's find the second derivative. Well, we're just going to take the derivative of the derivative. We're going to take the derivative of the first derivative, and we're going to call it the second derivative. And so this function, this quadratic function, has the property that its second derivative is equal to 2. And we're going to look on a graph and try and understand what that means. What does it mean if the second derivative is equal to 2? But before we do that, we're going to look at this with Liebnitz notation. Again, you need Leibniz notation. You're going to see it in upper year. You're going to see it in this course. So now is a good time for you to learn it. It's not particularly hard, as you saw in the previous video. So the second derivative with Leibniz notation, it uses square. So it's got these little 2's floating around, but it's actually not squaring anything. Those are just symbols. If we think of our previous example, we had the second derivative was equal to 2, and in Leibniz notation, that's how we would signify it, with these little square terms. There's also some alternative ways we could do it. So you see down here, I could drop that extra x and just have the f there. We could have the f of x off to one side like that. And then if we have an actual function like this one, I could write it like this if I was so inclined. Now, I hope you remember in a previous video, when we were doing the introduction to calculus, we talked about how the derivative of the function told us whether the function itself was increasing or decreasing. Specifically, whether it was increasing or decreasing at a specific value of x. If x was equal to, say, a, or x was equal to 4, something like that. And more generally, we can say it was increasing or decreasing on an interval, if we want to look at, say, an interval from, say, a to b, something like that. Now, what does the second derivative tell us? So if the first derivative tells us if the function itself is increasing or decreasing, then the second derivative is going to tell us if the first derivative is increasing or decreasing. Right? You could just kind of imagine that, we know that this is, f prime is the first derivative, but of course I could just tell you, just have some function for that, right? And if you took the derivative of that function, you'd know whether that f prime was increasing or decreasing. So let's walk through this just a little bit, and I'll introduce some terminology. So suppose, like in our example, we have f double prime f prime prime is greater than 0, then is f prime increasing or decreasing? Well, it must be increasing, right? The rate of change is positive, so f prime is getting bigger, and f is convex if f double prime is greater than 0. We call it convex. If the second derivative is greater than 0 or equal than 0, we say that it is convex. Now, what if we have a second derivative that's less than 0? Then f prime is decreasing, and this implies f is what we call concave. And it's concave if f double prime is less than or equal to 0. So we say that it is concave if the second derivative is less than 0. If it's a negative value, we say that the function is concave. Now, the last one is kind of a trick, but one that students always ask me. What happens if f prime is equal, f double prime, f prime prime is equal to 0, then f prime is constant, or I should say then the rate of change in f prime is constant, and f, the function, is both concave and convex. And maybe I'll just add example, a linear function y is equal to ax mx plus b has a f prime prime equal to 0 and an f prime equal to m. And so it's a linear function is both convex and concave. Now let's look at some graphs and make sure that we really understand how to interpret the first derivative and the second derivative. So here we've got x and y axis, and we've got this curve, and it's curving upwards. So if I were to, draw some points of tangency on here, going like that, is f, and this is f, right? F of x. Is f of x increasing or decreasing? Well, it's increasing, right? It's getting bigger, as x increases, right? As x gets bigger, y is getting bigger. And if that's the case, then f prime is greater than 0, right? The rate of change in this function is positive. Now, is f increasing or decreasing at an, or I should say, is f increasing or decreasing at an increasing or decreasing rate? Well, we know that f is increasing, so that gives us the first part. F is increasing. And is it increasing at an increasing rate or a decreasing rate? So is the slope becoming steeper or more shallow? And you can see by the tangent lines that I've drawn that the slope is increasing. So F is increasing at an increasing rate. And I can take off this little question mark. So F is increasing at an increasing rate, and F double prime is greater than 0. So F is convex. And if the second derivative is positive, then we say that F is convex. That's the word, that's the terminology we apply. Now let's look at our next function. Is F increasing or decreasing? Well, as x gets bigger, y seems to be getting smaller. And so we can say that F is decreasing. Or maybe I'll just scratch out the incorrect one. So it's F is decreasing. So we know that F prime is less than 0. And is it increasing? And so we know it's decreasing, so I can get rid of this one as well. Is F decreasing at an increasing or decreasing rate? Well, if I kept drawing this function along its trajectory, it would be getting larger, right? If I draw some tangency points over here, we can see that the slope is becoming, I guess, less negative. If that's a mathematical expression, the slope is increasing, right? It's becoming actually less steep. The value of the slope is becoming larger as x increases. And so F is decreasing at an increasing rate. So F prime, the second derivative, is greater than 0. And all right, I hope that you're getting the hang of this. Maybe I could ask you to do it yourself. If you want to do it yourself, by all means. But let's take a look. Is F increasing or decreasing? Well, if I increase x on this interval, y is increasing. So F is increasing, which means F prime is greater than 0. And so we know that the first part of the second sentence is increasing. Now, is F increasing at an increasing or decreasing rate? Well, again, if I draw the little points of tangency, like so, and like so, or if I continue to draw this function the way that it's going, it should be clear that as x increases, this function is, the curvature is negative. So the second derivative is negative. The slope is becoming more and more flat, or becoming more and more negative. And so f is increasing, but it's increasing at a decreasing rate. Let me get rid of that. And so we have f prime prime is less than 0, and so f is concave. One more. Is f increasing or decreasing? Well, it should be clear by now, I hope, that it's decreasing. If x increases, y decreases. If x increases, y decreases. And if we drew those little points of tangency that represent the slope, you can see that it's becoming more and more negative. And so f is decreasing at a decreasing rate. So we've got f prime, is less than 0, and we've got f prime is greater than 0. I'm getting tired. I'm making mistakes. So the function f is concave. And here's a summary slide. If you just want to take a look at it, help you study. I already answered the last question. What if the second derivative is equal to 0 on the interval I? Then f is, small f is both concave and convex. It's both. Now, let's go through a little formally without looking at the diagrams and evaluate the following functions to determine their concavity and their convexity, and maybe whether they're increasing or decreasing while we're at it. So we've got a negative cube function. Wow. So the first thing I'm going to do is I'm going to find the first derivative. So maybe I'll write it in Liebnitz notation. dy over dx is going to give me negative 3x squared. And then I want to find the second derivative, like so. And I'm going to take the derivative of this thing again, and I'm going to end up with negative 6x. And now I need to interpret it. Right? And we can see here that x is strictly positive, or 0. And so we don't need to worry about the 0. Let's just focus on the case where x is greater than 0. So if x is greater than 0, I'll stay in Leibniz notation. Dy over dx is is less than 0, right? If x is a positive number, in fact, in this case, because it's squared, even if it wasn't, this term here is always going to be positive. This is our negative, and so dy over dx is also going to be negative, no matter what. What about our second derivative? We've got negative 6 if x is strictly greater than 0. then x is going to be positive. We've got a negative over here, and the second derivative is also going to be strictly negative. And so we can say that y of x is decreasing on the interval I, and y x is concave on the interval I. This is our definition of concavity. And now here's an example. Why don't you determine if the following function is convex or concave on the interval where x is greater than or equal to 0. Okay, I hope you've solved it for yourself. Let's walk through it together. We've got dy over dx is equal to negative 2 over 3 x negative 5 over 3. And, ooh, this is going to get ugly. The second derivative going to get negative 2 over 3 times negative 5 over 3 times x negative 8 over 3. And we know we're interested when x is strictly greater than 0. If x is 0, not much going on. And we've got this thing is positive. So remember that x negative 8 over 3 is equal to x 3 over 8. And that's going to be a positive value. So it's positive. And then we've got a negative and a negative. And if we've got a negative times a negative, that's going to be a positive. And so if x is greater than 0, d2y dx2 is going to be greater than 0. And if it's greater than 0, that means that it's convex. And we know that dy over dx, you've got a negative here. This x is always going to be positive. And therefore this is less than 0. And so f is decreasing and convex on interval I.